Okay, in this video, we're going to talk some more about ionization energy, but we're going to talk about exceptions to the periodic trend for ionization energy. Okay, exceptions, to the periodic trend for ionization energy. So I have a little XY axis here, and on the on the Y, we're going to plot ionization energy. And we could give it units, it's just kilojoules per mole, but we're not going to deal with numbers. Just going to look at the general trend. Now on the x-axis, we could plot nuclear charge. And again, this is just general, we're not plotting any numbers. So let's plot, let's just start in the second row of the periodic table with lithium, and we'll plot it down here, and that's lithium. Now, what we would expect is things to just gradually increase as we go. So lithium is there, beryllium would be there. We would expect boron to continue this straight line trend and be, I don't know, up here somewhere, but that's not what we see. Okay, what we see is that boron is down. And then as we go, carbon again goes up. And then nitrogen again continues that straight line trend like we would expect. But then we come to oxygen and it dips back down. And then the rest of them, fluorine and then neon, are what we would expect. Oops. I assume you guys are used to me making mistakes in class, so no big deal. So if we connect the dots, we see this jagged line. We don't see a nice straight line that we would expect. Okay. In highlighter, I'll do what we would expect. The periodic table, or the periodic trend, we would expect to see just kind of a straight line from lithium to neon, but we see kind of this jagged line. So let's go through each of those differences one at a time. So let's first take this beryllium boron exception, and let's talk about that. Okay, down there we'll talk about that. So what we're going to do is we're going to look at beryllium and boron, and it shouldn't be any surprise that I'm going to do the electron configurations, 1s2, 2s2 for beryllium, and for boron, 1s2, 2s2, 2p1. So there's the difference, is that 2p1 electron for beryllium versus boron. And if we go back and we look at the ions, Be plus 1, we see that it is 1s2, 2s1. Okay, we removed a 2s electron. And then for boron, same thing, we're just going to remove that valence electron. 1s2, 2s2, and that's it. We've removed the 2p electrons. So that's what we're removing for boron. And the p is further from the nucleus. Than the 2p, so it's easier to remove. Thus, it is easier to remove an electron. And that's all it is. The p is further from the nucleus, so that electron just comes off with less energy than what we would expect. Okay, pretty simple. So now let's go back up to our graph up here, and let's deal with the next exception, the next anomaly, and that's that nitrogen-oxygen anomaly. So that'll be down here somewhere. Whoops, that didn't work, did it? Like I said, I'm just getting used to this. Okay. And we're not going to do electron configurations. What we're going to do is orbital diagrams. So if we do nitrogen, we have the 1s, the 2s, 1, 2, 3. Remember, in this class we never can forget what we've learned in the past. So orbital diagrams, electron configurations are important. Okay, so there's nitrogen. What would nitrogen plus be? Pretty simply, N plus 1s, 2s, 2p, and we're just going to remove one of those 2p electrons. Oop, that's the guy we're removing. Okay, and then for oxygen, do the same thing. 1s, 2s, 2p, 1s. And if you guys, I'm going too fast, you obviously know you can pause this and get caught up and write things down. Okay, so there's oxygen, O plus. 1, 2, 1, 2, 3. Again, 1s, 2s, 2p. And just one less electron. So again, which electron did we remove? We removed, oh man, I hit the erase button. And let's just fix that. There we go. We removed that paired electron. Why is it easier to remove the paired electron? Well, when two electrons are paired, they share the same region of space. And if they share the same region of space, that means they're closer to each other. And electrons both have a negative charge, like charges repel. Therefore, it is easier to remove that paired electron from oxygen than it is to remove the unpaired electron from nitrogen. And that is why we see that little anomaly right here in the periodic trend. Okay, that's all for now. We'll a little bit more about ionization energy in the next video.